Okay, so hi, it's great to be here. I'm so excited to be back in New York. I haven't been here in forever. It's such an amazing city. People are dressed so nice, unlike where I live now. So it's great to be here. Before I start talking about science, actually, I want to talk about something that is near and dear to my heart. So this is a book. It has a swear word in the title. I apologize. But I do actually think this is a really important thing. You know, a lot of us complain about like all the, sorry, old people, any old, like people who are close to, people who are close to retirement, they're mean and they're nasty. But the thing is like, we get to decide now what the culture of our field is going to be. It's up to us, like, if we want a place where everyone is nice to each other and supports each other and is constructive, like that's up to us now. And so I think it's really important whenever possible to try to treat each other with kindness and respect. I also think that will help with inclusivity. This book is really interesting and I can highly recommend reading it. The argument it makes is that this guy is a social psychology professor, business psychology, and he demonstrates that there's actually, even if you think someone who's a jerk is like really effective at their job, they have such a negative net impact on the overall workplace that they significantly diminish productivity. So even if someone seems really productive, it is not worth hiring them if they are an asshole. Don't hire them. So I just wanted to plug that and plug also just remember to treat each other with kindness. That being said, as we heard this morning, I may be saying some controversial stuff today. So if you want to just skewer me, you are absolutely welcome to. I can take it. So that's not to say like be nice to me about scientific results. You can absolutely skewer me. Okay, so today I want to talk about, I want to give a little history about kind of the study of extragalactic astrophysics before James Webb. I'm not a really historian, so if I mess it up, you can feel free to let me have it. Then talk about some new discoveries with the James Webb Space Telescope, in particular, very massive galaxies at very early times, potentially. Then talk about how some of the new methodologies we're developing that enable us to get more information out of James Webb data more efficiently, in particular slitless spectroscopy and also spatially resolved studies of galaxies using some new methods we're trying to develop. But before I talk about any of that, I'm going to be talking to you about distant galaxies, but we're going to start a little closer to home, my home in Boulder, Colorado, which, as it happens, is the land of milk and honey. You should all come and visit. It is absolutely fabulous in Boulder. But also in Boulder is Ball Aerospace. So Ball Aerospace is where the engineers spent years creating the 18 gold-plated beryllium mirrors that make up the primary mirror of the James Webb Space Telescope. So a few years ago, all of these beautiful mirrors were shipped from Ball Aerospace in a big shipping container. They're flown in an aircraft carrier to the Goddard Space Flight Center in Maryland, where they were assembled into this enormous golden mirror, this iconic golden mirror, which is 21 feet across and is the largest mirror we've ever launched into space. So work on this thing began in 1996. Is there anyone in here who was born after 1996? Yeah, your whole life. People have spent the entirety of your existence working on this telescope. You're welcome. I'm not one of them. Yeah, I'm not that old either, but this thing has taken forever. It's immensely complicated. Work on it spanned the entire globe. It's really a story of international collaboration that we were able to build this thing. So, you know, we're talking over 2 decades, $10 billion. And finally, this thing was ready to go. Very, very late. It was shipped down the Pacific Ocean through the Panama Canal to French Guiana, and then it was folded up like origami and put on this rocket and launched into space on December 25th, 2021. Oh, I was hoping the sounds would work. That's not. Is that working now?
Nope.
It's French.
And we have engine start. And liftoff. Decollage, liftoff from a tropical rainforest to the edge of time itself. James Webb begins a voyage back to the birth of the universe. Punching a hole through the clouds, 20 seconds into the flight, good pitch program reported.
So I did, in fact, make my parents watch that launch with me. It was Minnesota, so it was 6 a.m. and I was like, you will drink champagne with me. Like, it is 6 in the morning. I'm not sorry. So with most programs, the launch constitutes most of the risk of the mission. With James Webb, that wasn't true. There was 300 single point failures. There's all these deployments because this is such an ambitious program that required all of these crazy components to be developed and not fail in order for us to actually be able to see back to very close to the beginning of time. So as this thing is hurtling through space, you know, it's unfolding this tennis court sized sun shield, each of these layers about the thickness of tinfoil. And then it has to also deploy this mirror with very exacting specifications, you know, getting it perfectly aligned to, you know, 1/400th the width of a human hair, all while it's, you know, flying thousands of miles an hour, and we can't fix it if we mess it up. So that's the real scary part. So we were all very scared during these 30 days of terror, I think they called it. So this is a really remarkable development. And the fact that it succeeded is the really, really remarkable part. I figured I was going to get fired when this thing blew up on the launch pad. But you know, because they're like, what do we need you for? But it works, and it works even better than we expected. But I think one question, especially theorists may want to know, why did we do this? Oh my God, this thing is $10 billion. It took 2 decades. It's this incredibly fragile, incredibly expensive piece of machinery that we're sending 1 million miles away where we can't fix it. Why are we doing this? What is it that this is actually going to allow us to learn that we couldn't learn without it? So I want to briefly tell you the history of how we got here, because I think it's interesting and illuminating. So this is in, actually, I'll just ask you, a bunch of theorists, you know what this is?
Edwin Hubble.
What is it?
Edwin Hubble's discovery of the Sept variable in Andromeda.
Yeah, at least one person knows what this is. This is Andromeda. You may remember the really nice picture of Andromeda that was Mac background for a while. This isn't that, but you know, this is a picture of Andromeda, and it has these ends noted on it because Hubble thought that all of these stars were novae. In fact, one of them is a Cepheid variable star, which is why he crossed out the N and put the var exclamation point. And so then using Henrietta Leavitt's period luminosity relationship, he determined that Andromeda is not actually a cloud in our own galaxy. It is an entirely separate galaxy. And in fact, there are a lot of galaxies in the universe, but it was with this discovery that our entire universe went from being just the Milky Way to an enormous universe of galaxies. It completely changed our understanding of our place in existence. So, you know, sometime later, they named a telescope after this guy, Hubble, was launched in 1990 to get basically a more detailed view of relatively nearby galaxies. But when we actually launched this thing and were able to look at the new view it provided of the universe, things were much different than we thought. So there was this director's discretionary program that wanted to look at a single empty patch of sky for about 2 weeks, I think. I might be messing that up. A long time, which, you know, that's a horrible idea, right? Like, who would, you know, you're taking this immensely valuable resource and you're looking at this empty patch of sky. So people are pissed. So I hear, I wasn't around then, but when you actually look at this, of course, this is the Hubble Deep Field, and there are thousands of galaxies. So this empty patch of sky turned up thousands of galaxies. And there was a number of surprises when we actually were able to look at the distant universe that we weren't expecting. So two things in particular. When you could look back to these early times, there was actually old galaxies. We weren't expecting that because we thought galaxies took a long time to form. And so we were not expecting old galaxies at early cosmic times. The other thing, which this is what I was told, maybe it's wrong, but according to someone who I think should know, some of these galaxies, you know, they look, they're complex. They don't look like galaxies in the local universe. And so according to the story I heard, one famous astronomer that you all know apparently said, oh my God, they're a fucking mess. And that is the story of how extragalactic astronomy began, the study of galaxy formation, because we realized that galaxies actually do evolve. They're not just island universes that, you know, form and then just sit there, right? They go from being these messy structures to the regular, beautiful bulges and disks and ellipticals that we see today. And so it was with these things that James Webb was conceived, because we realized we needed to actually be able to look even further back in order to see the earliest stages of galaxy formation. So this is why we sent James Webb into space. We want to understand our cosmic origin story. We want to be able to see the formation of the first galaxies. The universe was formed about 14 billion years ago, and then we ended up here with all of these structures, stars and galaxies and tables and chairs. How did that structure emerge? And I'm interested in this question, obviously, on large scales and the scales of massive galaxies in particular. And so that's what I'm going to be talking to you about today. So most of you are galaxy people, right? Yeah, can I see a show of hands of who are the galaxy people in here? Most, about half these. Okay, cool. So I'll try not to bore all you people who don't like galaxies. So this is, so just so we're all on the same page here, galaxies, in my humble opinion, are the building blocks of the universe. They, in the visible universe, there's about 2 trillion of them. They contain all of the stars, planets, black holes we think in our universe. They're not island universes. They interact with their environments. These are cosmic recycling plants. Essentially all of the metal content in the universe was generated through star formation in galaxies. And their formation is very complex because of the huge range of time scales and spatial scales that is relevant for their formation. To actually fully model it on the relevant scales, although, you know, Shai can feel free to disagree with me here, would require all of the energy from the sun. So that means that we need observations. We need to actually send telescopes out into space and look at these things. So I think that in particular, large space-based telescopes are one of the best tools we have for understanding the formation and evolution of galaxies. So galaxies kind of have two key components. You have a bulge, which is, whizzing bees in a beehive, and a disk, like a, rotating, sparkling pinwheel of stars. And so one of the things that we want to know is, how do galaxies form these two kind of key structures? And so this is a picture of Andromeda. Andromeda, like the Milky Way, are pretty typical galaxies in the sense that if you're a random star born in the universe, you are a star. You would likely be born in a galaxy like the Milky Way or Andromeda, in terms of how massive you are, in terms of how massive those galaxies are, and also being in a bulge disk system. So the reason this is hard to figure out how these different structural components formed, how galaxies evolved, is because most galaxy growth happened in the past, right? Galaxies are growing at a very small fraction of the pace now that they were at early cosmic times. So fortunately, there's a solution to this. There's two solutions, actually. You can either do galactic archaeology. You can study the stars in the Milky Way in great detail to understand how they, you can study their chemical compositions, their velocities, and put together a history of how those things arrived, where they are and how the galaxy formed. The other option is you can do look-back studies, which is like, fossils versus live dinosaurs. What do you think is cooler? Obviously, I think dinosaurs are cooler. So the reason you can actually look back to early cosmic times is because telescopes effectively act like time machines. Light takes time to travel. So if you're looking at something that's really far away, if you have a very powerful telescope to do that, it is like looking back in time. So we can actually look back in time to these very early cosmic times to watch these galaxies form. This is, as a sidelight, something I found so fascinating when I was a child, that it is why I'm here today. I did a report on the Hubble Space Telescope and then did my PhD thesis on it. The reason that this, I was an ugly kid, yeah, I know. You don't have to say it. So look at, I mean, come on. So the reason, yeah, it was a rough, it's an awkward few years there. Okay, so one of the challenges, though, as we're looking back to these early cosmic times, is the universe is expanding, and so the light from these early cosmic times, which has been traveling a long time through space, gets stretched out as it comes to us. So when we want to look at galaxies which are forming at really early times, we have to be able to look in infrared wavelengths. So we built the Spitzer Space Telescope, which showed us a lot of distant galaxies. As you can see here, they're beautiful. So Spitzer was actually really great, but it didn't have the sensitivity or the resolution for us to really be able to study early galaxies in detail. Does anyone know what this is an image of? No? Wait for it. Now, do you know what's in it? Now, do you know what's an image of? Yeah, so this is the first JWST image that was released by President Biden, like painfully late last summer. We were all like sitting there on Zoom, we're gonna celebrate, it was gonna be awesome. We had our champagne, and then, half a bottle of champagne later, Biden has still not released this image. So, we're just sitting there, it's awkward. But the resolution going from Spitzer to James Webb is just remarkably better. So you can really see that not only are these images much deeper, and so there's all of these distant galaxies that pop out of the noise, but also you can actually see what these things look like. And it's really the first time we've been able to actually see what all these different objects look like. This guy, that's a redshift 10 galaxy, I believe. And it isn't even there in the Spitzer images. So what we can do with James Webb is just really remarkable. And so the first results that are coming out of James Webb, these early results have been very surprising. You know, Chris may just want to tell us that none of it's real, which, you know, he's probably right about some of that. But the results have been very surprising. So, okay, we talked about the universe before James Webb. Now we're going to talk about these objects that, these candidate objects that might be too massive too early. So we know based on our simulations of the universe, this is from TNG 300, that the universe essentially, well, starts as fairly uniform, and then gradually small structures build, and then larger and larger and larger structures build. So at early cosmic times, you expect most of the things to be fairly small because that is how structure forms. It's hierarchical. So you may understand my surprise, although not initially when you see this picture, when I saw this puppy in the in the first JWST imaging. So we were looking at things that were like bright and red, and we couldn't see them in Hubble. And my friend and collaborator and I, Rachel Bazanson, were starting to do stellar population synthesis fitting for some of these red objects. And one of them in particular, this one, ended up with a stellar mass estimate and redshift estimate that put it at odds with what we were expecting based on cosmological simulations. So this thing has a stellar mass of about 10 to, or our first estimates had a stellar mass about 10 to the 11 at a redshift of 9. So, you know, doesn't make a lot of sense to people who don't study galaxies. That is very high redshift and a very high mass. So once we found this, we were all very excited. We slacked our collaborator Ivo Labe, who was in Europe at the time and spent all night like trying to find more of these, and so found another 5 of them. And these things have completely different spectral energy distributions than objects that we had seen previously. So the previous samples that we were able to select with the Hubble Space Telescope and Spitzer, they're very blue relative to these objects. So these objects are just much, much redder than the previous samples we've been able to select. So they really have this qualitatively different kind of observational SED shape. So when you actually, fit the redshifts and stellar masses of these objects, there are about 6 of them, which have stellar masses of over 10 to the 10 at redshift 7 to 9. So that probably doesn't mean very much to most of you. And we selected them using this color technique, which you don't need to worry about. But the reason this is meaningful is twofold. So if you look at the number of things with a given mass in previous studies with Hubble and Spitzer, you get these cumulative stellar mass functions. When you add in just these 6 objects from JWST, they are way beyond the existing estimates of the stellar mass density in the universe. So the implied stellar mass density with these objects is an order of magnitude higher than expected from Hubble and Spitzer. So if these end up being confirmed, big if, they, a significant fraction of the total stellar mass density in the universe at these times may be in high mass galaxies or something else. But they really do add significantly to what we thought was a stellar mass density. So there also are expectations from a theoretical perspective. So you can make estimates based on cosmological models by painting baryons, by painting stars and galaxies onto dark matter halos in simulations. So this is a paper by Mike Boylan-Kolchin. I'm not a theorist, so I didn't do this. So if you assume a cosmic baryon fraction and an efficiency for turning the gas into stars, you can make predictions for where you expect, how often you expect to see galaxies of certain masses. So this is what you expect to see at a redshift of 9.1. And this is where these galaxies that we found lie. So a standard efficiency would be like this gray line. A high efficiency would be this brown line, and converting all of the available baryons into stars is this black line. And then converting more than all of the available baryons into stars would put you in this blue region. So the fiducial mass estimates we get for these objects push up against the limits of what this theoretical work say is possible. I suspect Chris is going to let me have it here, but that's okay. So these things definitely still need to get confirmed, but this was pretty exciting for us because this was something we really did not expect to see. So this was published in Nature, and then I think, people are excited about James Webb. So it was covered in a lot of different news outlets. So it's not just astronomers that care. I was in 60 Minutes, which was really fun. I got my hair done and stuff. It was really great. So it was really fun to just be able to actually, for people to actually care about something that we're doing with this really expensive telescope that taxpayers built. You kind of feel like a jerk when you're spending all this money and then not doing anything that anyone cares about. So it was cool to actually that people were interested in galaxies, which is cool. But that being said, we of course do need spectroscopy to actually confirm these things. My program to get spectroscopy was approved for cycle 2. So we will be getting data in January. So I will keep you updated on whether all of these things go away or if any of them are actually real. We already know that one of them is actually a baby quasar because the Sears program got spectroscopy last December. And so it's one of the lowest, at that point, it was one of the lowest mass black holes seen at redshifts greater than 5. Do we think all of the rest of them are baby quasars? Probably not, because they are spatially resolved. I forgot to update this. A paper by grad student Josephine Baggin published recently. She measures sizes for these things, and the only one that is unresolved and hence a point source and hence an AGN is the one that was already shown to be an AGN. So we don't think that they're all baby quasars. We don't know exactly what they will be. If even one of the masses holds up, one of the star masses holds up, it will remain impactful for our understanding of how galaxies form at early cosmic times. Some of these things, this was published, I believe this appeared on the archive 2 days ago. Meng Wan, who's a postdoc in Geneva with the Fresco survey, did actually get spectroscopic confirmation of three of these kinds of objects. These are at slightly lower redshifts, but have higher masses. So these are at all at about a redshift of 5 with stellar masses greater than 10 to the 11th. So these are in fact spectroscopically confirmed objects. They all are detected in H alpha with the Fresco survey. So these are them. So these 3 objects, so you can see They're very massive, they're high redshift, and these are them versus the theoretical predictions. So these also are much higher than theoretical predictions, which suggest that galaxies can exist with those densities. So if these are all correct, it does suggest that galaxy formation potentially began earlier than we thought, that we are able to grow these objects to very high masses at remarkably early times. There's a number of other lines of evidence that go in the same direction, although, you know, we'll see what happens. Early days yet. So this is from Steve Finkelstein's paper. There's been a number of other papers showing similar things, which is to say that there are we are seeing evidence that there are galaxies which are very luminous at very early times in high number densities. It could potentially be explained with bursty star formation, high UV fluxes, bursty star formation. The other potential explanations for this tension are that these are not actually at as high redshifts as the published papers suggest that they are. This has already happened once. A redshift 16 candidate was actually shown to be a dusty galaxy at redshift 4. So we really need spectroscopic confirmation. There's a number of cycle 2 programs that will be getting spectra of these things. So we will see how many of these actually hold up. Additionally, this is work by my very fabulous undergraduate student, Abby Hartley. She used the TNG 300 simulation to look at when the first galaxies quench. So you have these massive galaxies, they form early, do they quench early? So she found that the first quenched galaxies in this simulation were at about a redshift of 4, and already we're finding Katie showed results and has published a paper showing that there are, as well as some other authors that have shown there are quenched galaxies at even earlier cosmic times than are predicted. And so potentially, as we talked about at lunch, you are missing potentially some quenching physics in these simulations at these early cosmic times. So in summary of this portion of the talk, the galaxies might be chunkier than we expected. There's very few things more fabulous than a fat cat, like truly. Can you think of anything that is actually more wonderful than a fat cat? Because I can't. So we're seeing potentially, and this all requires more observational evidence and confirmation, but we're potentially seeing that things are more massive earlier than we expected. So we've talked about these galaxies, too fast, too furious. Oh, shoot, I was gonna put in a too fast, too furious slide. I love too fast, too furious. So next, we're gonna talk about the slitless spectroscopy and the slitless spectroscopic revolution. Y'all know what this is, yeah? That's Orion. So if you zoom in, maybe, on Orion, you can see Orion's belt and Orion's sword here. And in Orion's sword is a star-forming region. The red is H-alpha emission, which is gas ionized by hot young stars. Indicating that we are seeing stars which have been born on short timescales, or short by extragalactic astronomy standards, like 10 million years. So this red H alpha emission, Balmer alpha, where we can use as a tracer of star formation. So nearby, we can see these star forming regions in spectacular detail. We can even see them in spectacular detail in nearby galaxies. Andromeda again. So the pink is the star formation. So we can trace the spiral arms. We can see all of these individual star forming clumps. Up until, about a decade ago, the best that we could do to trace star formation, how galaxies are growing, how they're building up their stellar mass, was this. So you can see this beautiful resolution. So this is not resolved for all you theorists. This isn't resolved. So we didn't have the spatial resolution to actually be able to trace how galaxies were growing. This changed with the construction of 10-meter telescopes or 10-meter class telescopes with adaptive optics on them. So you can, with these instruments, you can trace, you can map star formation, but it's really expensive. The group at MPE did this really beautifully for the first time, kind of in the early 2000s. But the problem is it takes like, a night per object, which unless you direct an institute, you're not going to get that time to build up a normal sample of objects. So you can do this, but it's really expensive. But so up until kind of that point, we had about 50 objects where we could actually trace how they were growing at these early cosmic times when it's actually, when most of the star formation in the universe actually occurred. This all changed when they put the Wide Field Camera 3 on the Hubble Space Telescope in 2009. Wouldn't this be a cool job? Don't you want to be an astronaut when you see stuff like that? I do. So this was them installing Wide Field Camera 3 on Hubble. And when they, with this new instrument, there's this mode called a grism. So it's a grating prism. So it basically, it's slitless spectroscopy. So it allows you to get spatially resolved spectroscopy for every object in your field of view. So this was really game changing. So this allowed us to get spatially resolved H alpha emission for all galaxies in our field of view. These maps are beautiful. Trust me on this one. These are beautiful. Nod. Yep. These are beautiful, beautiful maps of star formation. And we can do this. So we went from being able to do this for 60 galaxies to about 3,200. And so this just has a lot of, this allowed us to do population studies and actually determine for the first time in a systematic way, how galaxies were growing at this epoch. So I'm not going to talk about any of these things in gory details, but we can use this to see how galaxies form their stars, how they quenched, how they grow in size, how they build their structures. So I developed this method as part of my PhD thesis. So one of the things we can do, which I'll just briefly tell you about, is that we can use this to map how galaxies are shutting off their star formation. So to do this, these observations are this black line. So this is the specific star formation rate as a function of the radius in a galaxy. So this is the center of the galaxy. This is out to large radii. And so you can map where the star formation is versus where the stellar mass is. So something that this kind of information tells us is about how galaxies shut off their star formation. So what I'm showing you here is a comparison of the data in the real universe to what we're seeing in the universes in boxes, namely from the illustrious simulation and the TNG simulation. So what you can see here is that although these profiles don't match with the data in the illustrious simulation, they do in the TNG simulation. And what we found was that seems in the TNG simulation to be driven by AGN feedback. And so without this kinetic wind AGN feedback, we're not seeing the centrally suppressed star formation we see in the real universe. So although there could be other ways that we could get this centrally suppressed star formation, this kind of information about how galaxies are growing and quenching can provide constraints on feedback mechanisms in simulations. So with James Webb, we're really able to, there's a bunch more GRISMs. Everyone loves the GRISM now. This is with the James Webb Space Telescope NIRCam instrument. This is a image in 4.4 micron emission. It is just absolutely beautiful. And then with the GRISM, we can disperse all of the light from these objects and get resolved spectra for all of the objects in the field of view. So this is actually a very low redshift galaxy. This is a pH feature. So this is a resolved pH feature in a low redshift galaxy. So we can do this for tons of galaxies now. This is a stack of all of the spectra ordered by redshift. And so you can see, we can trace how galaxies are growing across a huge span of cosmic history. You can see the bracket alpha, Passion beta, H alpha, and O3 H beta, all the way out to redshift 9. So from the local universe all the way out to redshift 9. And there's some really cool things that we can do with this to map how galaxies grow. This was at redshift 1. Jesseline Matharo, yeah, sorry, I couldn't help myself, I had to use the confetti. Jesseline Matharo is now able to do essentially the same thing, except at redshift 5. So we're seeing through her work, this is going to be published soon, that galaxies grow inside out also at a redshift of 5. You can measure the density of star formation in the center, how galaxies are building their bulges, how they're growing at these very early cosmic times. The thing I'm really excited about at the moment is that you can actually also use this to measure kinematics in galaxies. So this is an object we found in the survey. So this is an object at a redshift of 5.3, where we can actually measure a resolved rotation curve. So this thing is a spectacular object. It is rotating at about 250 kilometers a second at a redshift of 5.5. So that is that implies a very high dynamical mass. That's similar to the rotation rate of the Milky Way, except the Milky Way is now, and this is a billion years after the Big Bang. So we're actually seeing dynamical confirmation of these high masses at early times, which is really cool. I'm very proud of this methodology, so I'm going to just bore you for 1 second with it. I came up with this method for how to actually measure the kinematics here, using a combination of medium band imaging to get an H alpha map, so to get the actual spatial information, and then you can combine that with the GRISM image to get the rotation curve. And so it's this combination of medium band imaging and GRISM spectroscopy that allows you to get, in principle, to get kinematics also for every object in the field of view, which would be a remarkably efficient way to do kinematics at high redshift, which tells you about the dynamical state of the objects, and something about their formation history, whether they're rotation dominated or whether they're dispersion dominated, like galactic bulges. So this thing is also growing inside out, which is cool. You can map everything. It's really amazing. And finally, in the remaining -2 minutes that I have, just wanted to show a couple resolved results. So in particular, James Webb is, with its much higher spatial resolution, is allowing us to resolve objects in a way that we really just could not before. So the first thing I noticed actually in the James Webb results was these things that were not visible in Hubble. So, you know, you go, there's nothing, there it is, bam, these huge red disks. So these Hubble dark galaxies, these objects that were not previously detectable with Hubble, are, you know, have been a topic of interest for a while. They're highly dust obscured. We can see them in the submillimeter often, but we can't see them in optical emission. So they've been very mysterious. And up until this point, we've never actually been able to resolve them, resolve where their stars are. So we now we see these remarkably red, you can see this guy, these remarkably red disks. So we just did not expect to see disks like this. These objects, these really red, very dust obscured objects, we expected to be kind of compact, dispersion dominated, very dense objects. And we're, in addition to that, seeing these super elongated ultra red extended disks. It's very strange. We call them UFOs for ultra red flattened objects. Yeah, I know. Hey, I have not gone on the radio and talked about aliens, so, you know, points to me for that. So unlike some of our colleagues, so these things are, they have these, they're very, they have exponential surface brightness profiles. They're not, these big bulge dominated objects. This is a project my graduate student, Justice Gibson, is working on. He's almost done. And the other very strange thing is that they have high projected axis ratios. So if something, is spheroidal, is bulge dominated, you expect it to look round, whatever angle you look at it from. And these things, they always look flattened. And so that suggests that either they're prolate or they're just all disk dominated and we're seeing them edge on. We think it's the latter, probably. They also have very small color gradients. We're gonna skip this. So galaxies look different at different wavelengths. We're just going to skip all this so that we can have time for questions. Okay, but this is all to say that galaxies look really different in different wavelengths. In general, as we model things as just a single dot, we completely ignore all of this beautiful spatially resolved information when we're modeling galaxies. So now with James Webb, where we have this remarkable spatial resolution in the infrared, with a huge range of resolution at the different in the different wavelengths, we actually need new tools in order to be able to model the light. So we're in the PI of a program called PIRATE. PIRATE is not an acronym. It is there's a SED fitting tool called Prospector. And so we're like, Prospector resolved. And we're like, ooh, Prospector. Well, that sounds like how a pirate would say Prospector. So it's called PIRATE. This tool we can use to actually we're trying to account for a spatially varying point spread function as a function of wavelength, and actually be able to infer the spatially resolved stellar populations of galaxies. This is a challenging problem. We are working on it. It is not done yet. We have a very cool neural net emulator, which speeds up the fitting process because Prospector is just never going to be as fast as Cartex dense basis. So instead, we made a neural net emulator for Pirate, which is called Parrot because it emulates. Get it? So this thing speeds up this SED fitting by a factor of about 10,000, which is great. So my primary role here is this. Oh, come on, play. Oh yeah, there we go. Okay.
This man right here is my great grandfather. He's the first cat herder in our family.
Cats, don't let anybody tell you it's easy. Anybody can herd cattle. Holding together 10,000 half-wild short hairs, well, that's another thing altogether. Being a cat herder.
Yeah, so that's my job. I'm the cat herder. I wouldn't recommend it. It's an unpleasant job. But we're basically with this program, we're trying to be able to actually determine in a real physical way how galaxies grow, what their real distribution of their stellar mass is instead of just the distribution of their light. And with that, be able to actually be able to draw substantive conclusions about how galaxies grow and quench, because you can't just do that with light. You have to do that with actual physical properties like stellar mass and star formation. So in conclusion, galaxies are chunkier, diskier than earlier than we thought. The early universe seems to build them much faster than predicted. All of this requires confirmation, obviously. Grism spectroscopy is a powerful way to get a lot of very resolved physical information for galaxies cheaply, and the future is resolved. I'm hoping that we are actually able to develop a piece of software that allows us to truly understand a physical picture of resolved galaxy formation. Thank you.
So we do have time for questions. Bring questions in.
So, really quick question. I want to be sure I understand. Is that your masses that you're determining, these are just photometric masses of the mass light radiation? Right?
Correct.
Okay. You also have a measurement of the star formation rate. Star formation rate times the age of the universe system.
Yes.
So you said that you guys have been seeing some of these quench galaxies that have redshift 4 around there, or above there, for instance, the observations. On sort of what basis are you declaring them quenched? They have been forming stars in 100 million years.
To be clear, that was not my measurement. Yes, but Katie is actually Katie's the person to talk to on this, because I have not made those measurements. Most of them, I believe, are post-starburst, kind of like they've quenched recently, like in the past year, but I'm not sure what their actual cutoff is for how long they have had to be quenched at what specific star formation rate. Katie, is Katie here? Katie, do you wanna pipe up?
Yeah. I guess, I don't know, people kind of define it in really different ways. There's anywhere from like a color selection or a specific star formation rate.
So I see where you're going with this, which is that you are concerned that they are just in a brief lull of star formation. Yes, they're bursty. These are massive objects. So this isn't like that looser paper with, a redshift 7.3 stellar mass of 10 to the 7 object, which is still in a bursty phase. These are massive. These are massive objects. So, but I do see, yeah, but there is burstiness in the star formation, but it does. I think these things are mostly expected to be quiescent over longer timescales.
Any other questions? Yeah, Barrett?
I guess I have one, who also has his hand up.
Oh, yeah, I forgot about those people.
The Zoom people.
My question is, so,
Yeah, you'll get a question.
so if galaxies are getting too big too fast, does that mean, you know, in the early universe, does that mean that it's possible that galaxies in our current universe that are there, that we see them there, does that mean that they might have also formed faster, that they might be younger than we thought, or is there not a tension there too?
You mean so local galaxies formed earlier?
Local
Is that what you're
galaxies
saying?
formed closer to now than we thought. If you can get a galaxy to 10⁹ solar masses in some amount of time, then why aren't the 10 to, you know, does that mean that the 10⁹ solar mass galaxies that exist now also formed closer to now? Does that make sense?
I do see what you're saying. Yeah, and there's constraints.
Stars person, that's my caveat.
Yeah, stars person. Yeah, and I'm a high redshift galaxy person. So, you know, we're just both speaking in ignorance. I love it. So I mean, in principle, if you can form things really fast, you can. But I think the point here is that, you know, it is the physical conditions in these at later cosmic times are just much different than at these earlier cosmic times. And I think, you know, although we've been able to observe the physical conditions in local galaxies for longer because we've had telescopes that can study the star formation histories of galaxies at later times for a long time. These early objects were really just being able to infer their star formation histories for the first time now. So I haven't seen people say that, you know, 10⁹ galaxies in the local universe formed in the last couple million years, but there could be people saying that. I just haven't read those papers. But yeah, interesting question. Yeah.
We'll go to questions in the Flatiron conference room. Are there any questions in the Flatiron conference room? Yeah, sure. You can ask.
Okay, sorry, this is a question from a theorist, but could you talk a little bit more about how you are modeling the stellar populations in Pirate, right? These very early universe star formation, weird environments are going to produce unusual stellar populations that you're going to need to understand to pick out the star formation history, right?
Correct. Yes. So we're not using Pirate right now. Well, so Pirate, the main goal of Pirate is to actually be able to do things in a spatially resolved way. So we're really using that for things at likely somewhat later times that we have resolved information about. So right now we're using non-parametric star formation histories. That makes the computation extraordinarily slow, like really crushingly slow. So we might need to simplify our star formation history prescriptions, or potentially go to like a simulation-based inference thing or something like that. Yeah.
Okay, thanks.
I think you had a maybe different question that I didn't answer at all. So if that's the case, you can.
Well, I mean, I was curious about very early stellar populations, but if that's not relevant to the Parrot project, then we could talk offline or something.
Yeah, totally. Yeah, and for the star formation histories for for the very early galaxies, we modeled them in a bunch of different ways. We with a bunch of different assumptions about star formation history. We used non-parametric ones. We could not get those stellar masses to go down very much. Yeah, with whatever star formation history we used.
Okay, I'm gonna go to Zoom.
Oh, good. I was raising my hand for Barrage, actually.
Okay, yeah, that's so Zoom's turn now.
So
Barrage,
thanks, Stephanie. So just a very quick question. Great talk. Do you have any plans to get spectra for your UFOs to see whether the stars are in fact on circular orbits like you might expect for an oblate axisymmetric disk?
Yes, I would like to get spectra for the UFOs. I would very much like to get spectra for the UFOs. Yeah, because I would like to see if they're rotating. I'm hoping to sneak some of them in my program on the very massive potential galaxies. So I'm hoping to get spectra from that for them sneakily in that way. We also, but yeah, you might actually need either like IFU spectroscopy or if I can get something that's aligned right with a GRISM, then I could get it that way too. But yeah, it would be great. It would be really, really great. Maybe with ALMA, that might be another way to do it because then you'd also get the molecular gas information at the same time.